abstracts is better? Couldn't think of a math pun to that. This is a pun. The title's a pun. And it's not a pun on abstract. Hopefully by the end of the talk, we'll know why it's a pun. If I can do that, we succeeded. If not, well, then, you know, we still have pizza, so. All right. So what I want to talk to you guys about is about what mathematicians do, at least in some context. Okay, one of the things mathematicians like to do to try to understand what's going on in the real world. Because I think a lot of times when we just think about mathematics, we think about how it applies to real life situations. What kind of applications can we do? Engineering, physics, that kind of stuff. But mathematicians actually study a much richer, deeper kind of context, which sometimes then has other applications to the same ideas. And that's where I kind of want to go. And a lot of these things we're going to talk about today are motivated by doing arithmetic and the real numbers. How many of you are good at arithmetic? 3 of you. Very good. No. Okay. I appreciate your honesty and candor. I probably shouldn't have raised my hand either. Okay, but let's talk about arithmetic and the real numbers. Okay, so arithmetic. Am I writing big enough for those in the back? Manny, can you read that? Okay. Arithmetic in R. This right here, this boldface R, means real numbers. Okay, I'm going to use that a lot.
So like all real numbers?
All real numbers. All real numbers, everything, okay? Just one symbol for all of them. Let's talk about arithmetic in the real numbers. Okay, this is back to first grade and third grade. Is that when they do multiplication? Yeah, something like that. Okay, all right. So, what kinds of things do you do in arithmetic and the real numbers? What is arithmetic? Add, subtract. Right? We've got addition, we've got subtraction. What else we got?
Multiplication.
Multiplication, which will represent with the times dot or juxtaposition. Just means put it next to each other. And what else?
Division.
Division. Okay.
Powers.
Do you guys know what they call these? Operations. Very good. These are operations, arithmetic operations. How many are there?
4 so far.
I'm so proud of you. How many does it look like there are?
4.
Looks like 4, but how many are there really, Conley?
2.
2. Why? What 2?
Multiplication, addition.
Addition and multiplication.
I heard addition and subtraction, and I heard addition and multiplication. How many think it's addition and subtraction? How many think it's addition and multiplication? You're both right. No, depends on the viewpoint, okay? But the 2 operations that are that behave differently are addition and multiplication, okay? So there's really 2 operations here. Now, in the real numbers, you can define multiplication in terms of addition, and so in that sense, there's actually maybe only 1 operation, addition. But these guys do behave sort of distinctly different, and in mathematics, we do talk about them sort of as different abstract kinds of objects. So 2 operations, addition and multiplication. Okay, now we're really going to review your algebra, because I want you guys to help me figure out and remember what the properties of arithmetic were, the properties of addition and subtraction. So how do they behave? Nicely, right? Be good, children? I said it should be a question mark, right? Okay, so let's talk about addition. If I've got some real numbers, what are some properties of addition that you remember from either elementary school or maybe your first algebra course?
A plus B equals B plus A.
Okay, A plus B equals B plus A, and then we got associative, right? So A plus B equals B plus A. This is called what property?
Commutative.
Commutative property. How can I state the associative property?
A plus B plus C equal to A plus 1 plus C.
All right? And this is answering the question of what does this mean? Because addition is really a binary operation. It takes 2 numbers and gives you another number. So if I put 3 of them together, I need to know how to do it. And the fact that it doesn't matter which 2 I add first is what makes this operation associative. And I don't have an eraser. Good. So we got commutativity, associativity. Any others?
Identity.
There's an identity, right? Okay, so A plus 0, right, is the same as 0 plus A, which of course we know from commutativity. This equals what?
A.
A. So why do we call it the identity?
Because it keeps it the same after the operation.
Yeah, it doesn't change anything. Yeah, you do the operation, gives the guy back, right? Okay. What else? There's one more significant one on this. What's that?
Additive inverse.
Additive inverses. Boy, everybody knows where this talk's going. Additive inverses. Okay, what's the additive inverse of A? Negative a. What is, if I add the additive inverse to it in either order, where does it get me?
Identity.
Nowhere.
To the identity. Okay, so this is the identity the additive identity is 0. This is the identity property, this is the inverse property. Okay, how about multiplication? What are the properties there?
Associativity.
Associativity.
Kind of.
So that'd be like AB times C. The same as if you do the product BC first and then A. What else? Commutativity.
Sometimes.
What else?
It has an identity as well.
It is. What's that identity?
Oh.
1. A times 1 is the same as 1 times A, which gives back A. And then what else?
Every non-zero element is a unit.
Ah, I have no idea what that statement means. Come on. Yeah.
I'm gonna be the stupid one in the room. So if you do A, or like put the A and C together and then the B on the end, is it still the same?
Yes.
Okay.
Okay. But only because we have this commutativity kind of thing going on. Because you can rearrange the order. That's this guy says you can rearrange the order. And then this one says that once you have the order, you can do it in any sequence. Does that make sense? Okay. Now, we got the identity here.
Multiplicative
And then
inverse.
multiplicative inverse. What's the multiplicative inverse of A?
1 over A.
1 over A. We sometimes call this the reciprocal, right? Okay, and it doesn't matter which way you put it. Where does it get you?
Identity.
Back to the identity. Okay, now before we go further, can anybody see where subtraction and multiplication are on the board? Sorry, subtraction and division are on the board.
And the inverses.
Yeah, they're the inverses. This inverse property is actually telling you what happens with subtraction. There is no such thing as subtraction. You're adding the additive inverse of something. Okay? How about division?
Multiplication.
You're multiplying by the reciprocal. Anybody ever wondered why when you do 3/5 divided by 7/16, why you only flip the second one? The reason why is because it's the one that has the division sign in front of it, and division means multiply by the reciprocal. So its definition is in fact multiply by that. That's why you do it. And that's why it's only the bottom that gets flipped. First guy didn't have a division sign in front of it. Does that make sense? Okay? So that's where subtraction and division are. They really aren't a thing. There really is just addition and multiplication. Now we're not done yet. There's still some properties here, right? We've got properties of addition, we got properties of multiplication. Do they ever talk to each other? Yeah.
Distributive property.
Distributive property, frontwards and backwards. So this is together, I guess. Would be equal to AB plus what? AC, great. And if I did it the other way around, if I put the sum in front, same thing, right? What does that become?
AB plus BC.
AC plus BC, right? And then what happens if I multiply by 0?
You get zip.
Yeah, you just get 0, and that doesn't matter which way I do it. One thing I should point out here, I forgot to say, A is not equal to 0. Although Greg did say that, so. Okay, great. So these are the properties we have. What do you notice about these 4 here?
The common.
Basically the same.
Are they the same thing? The only thing that's different is the fact that I put a different symbol in between the numbers, right? But that's the exact same behavior that you're seeing there and that you're seeing here, right? That's kind of curious. Anybody find that weird? I do. Okay. Do you see addition or multiplication in any other setting?
Matrices.
Matrices. You can add matrices. How do you add matrices together?
Element-wise.
Element-wise, component-wise, right? Can you multiply matrices?
Yes.
Under what conditions?
The inner dimensions are matching.
Right. The rows of one have to match up to the columns the number of rows of the first one have to match up to the columns of the second one. I have to think about it. But yeah, right? If they line up just the right way, there is a multiplication that's defined in terms of matrices, right? Does that multiplication behave this way?
No.
What fails?
AB does not equal BA.
Yeah, it's definitely not commutative. Okay? Is there always an inverse?
No.
No, only if you restrict to square matrices do you get an inverse, right? Okay, so there's a little bit of something different that's happening with that multiplication than what's happening with the real numbers, okay? So the first level of abstractification that mathematicians do is they say, well, I know this stuff is acting in the real numbers. I've got addition and subtraction and multiplication in other places. what about them is the same? Okay? Because what about, let's talk about matrix addition for a second. Does it follow all these rules?
Yes.
Yeah, so if you have matrices all of the same size, it follows all these rules. That operation's commutative and stuff. So it's like it has these rules in addition, but it doesn't have these rules in multiplication. So that's a little funky, right? So the first idea that mathematicians do to try to abstractify this is they try to say, well, what happens if I only have the rules? What kind of things can I say? Because if I only depend on the rules of the game, then any game that has those rules necessarily has all those same truths. Does that make sense? So as soon as I find a place that has those rules. So really what it is we figure out what's happening, what's coming right from those rules. Sometimes we call them axioms. And we're going to build them out of these ideas. So the first set that we're going to take is we're going to look at these rules here without necessarily that one. Okay? And this forms, in mathematics, what we call a group. I think I want to put these over here. You don't have to follow me, Brian, sorry. All right, a group in mathematics is a set of objects. It doesn't even have to be numbers. It could be chairs in this room, okay? It's a set G with an operation that we'll call for now multiplication that takes an element in G and an element in G together, two numbers together, don't worry about times in between, just saying that I take one from each piece, and produces another element in the group, okay? It's operation. So just like multiplication over here takes two real numbers, and if you multiply them together, what do you get? Another real number, right? So that's exactly what this idea is. It's an operation that's going to take two elements of the group and produce another element of the group. Does that make sense? Okay? And it has to follow certain rules. The first one, which is kind of redundant, but for all A and B, this means N, in G, the product between them is also an element in G. That's basically this statement here. So if you take a product, it stays in G. Sometimes it's called closure. Okay? The second requirement is that it's associative. You get that same requirement over there about how multiplication behaves in the real numbers. The third one is that there is an identity element. I don't know if it's going to be a 0, because if you look, the identity element over in addition was a 0 and behaved that way, but in multiplication it was a 1, which kind of behaves a little different, right? So instead of giving it a name, a specific name, I'll say that there is an element, and I'll just call it E in G, such that A times E equals E times A gives back its own self, right? So some element behaves that way in the group, okay? Number 4 is that for every, wow, this got away from me, for every element A that's in G, there is an inverse element. And since we're talking about multiplication, we're going to borrow some notation from there. How do you denote an inverse in multiplication in the real numbers? How do you make a reciprocal?
Power negative 1.
Yeah, you can do what?
Power negative 1.
Power negative 1, right? So I'm going to have an element here that I'm going to denote as a to the negative 1, which just means inverse of a. Okay? The exponent itself doesn't mean anything, such that you have this property, that if you multiply those two together, you get back to the identity. You see how I'm copying almost exactly the same rules that you see over there, except that I skipped one. What did I skip?
Commutative.
Commutativity. It turns out that some of these things don't always commute, and so we want to have a way of studying both different types. Okay? So we can add in the fifth one, but we call that a special kind of group. An abelian group, that's the word for it, an abelian group adds in the requirement that, we'll say 5 here, that AB is equal to BA. Okay? If you don't say the group's abelian, you don't necessarily assume that, okay? Which means multiplying on the left, might not be the same. Kind of like matrices, right? The order matters. Okay? This is what we call a group. Now, what do you notice about this? How many operations did it have? Just one, right? Okay? How many operations do I have in the real numbers? 2. Now, if you look, if I forget multiplication for a minute and only think about addition, the group over there has this rule, and this rule, definitely. And it's clear that if I add any two real numbers together, I get a real number, so it has the first one too. And it in fact has commutativity. So if I only think about the real numbers with addition, what do I have? An abelian group. Okay, so that's an example of an abelian group. Something that follows all of those rules and is commutative. Does that make sense? Matrices with addition, is that a group? Just addition. Square matrices of all the same size, oh, they don't have to be square. Matrices of the same size with addition, does that form a group? Yeah. Steve, right? Can I see your bag? Or open your bag up. What do you got in there? I've got a little I got a volunteer here. What is that? A Rubik's Cube. A Rubik's Cube has symmetry in it. Okay? I can do moves to the Rubik's Cube that change a position but keep the thing still square. All right? Okay? Each one of these moves can actually be thought of as doing some kind of operation on the thing here. So what I'll do is I'll think of each state of the cube, each possible state of the cube, as, well, sorry, each movement on the cube as being a group element. Okay? I'll say not doing anything to it, starting with a solved cube, is the identity. If I move one spot, that's one element of the group. If I move a different spot, that's another element of the group. Okay? So the operation of adding them would just be doing them would be doing them in succession. So this one and then that one, which isn't very interesting. But what if I did this group, this one, and then that one? Okay? See how I added two together and it created a new state of the cube? Okay? I would call this new state sort of the addition of those two operations. Does that make sense? Of those two pieces. Okay? Now watch. I did this one first and then the top, right? And look at the state that's there. Look at what's on the top. I haven't tried this before, so I'm not sure it's going to work. Okay. What happens if I do them in reverse order? So I do the top first, and then I rotate that. Does it look the same? I really hope it doesn't, because I didn't look the first time. Does it look the same?
It's different.
It looks different. What does that tell you about what type of group this is? It's non-abelian. It does not commute. But it does, in fact, have the other properties. These operations are associative, and they're also, there's an identity element, and all that kind of jazz. So on a Rubik's Cube, there's a representation of a group as well. Okay, well this is really cool, because this means that if we understand how these rules behave, then we can actually understand the structure of a Rubik's Cube. And look at that, we totally just got this from the real numbers. We said what was special about the real numbers, peeled it off, studied it a little bit, and then realized, oh my gosh, the same exact structure is sitting right there in a game that people have been playing since 1984. Right? I don't know, is that when it was invented? Yeah. Okay.
Ish, yeah.
Sometime around there. Okay, does that make sense? So, where'd my markers go? There we go. Now, again, so that's really cool. It should hopefully show you that abstractifying a little bit does tell you about things structured in other places. But again, coming back to the same point, we only did one operation there, but I've got two here, right? And they behave, not only have some of these rules here, but they also have some rules of interaction. Okay? So let's study an object that has two operations then, and make some rules on how they interact. Does that make sense? This is what we call a ring. A ring is a set R with two operations. One that I'll call plus, but it doesn't really mean addition. I mean, on a group, it was twist, right? So it doesn't have to necessarily mean anything arithmetically. It takes two ring elements and produces a ring element. And then there's also a multiplication that takes two ring elements and produces a ring element. Okay? 3 rings. It's like Barnum and Bailey's, right? Right. That's funny. No, anyway. All right. There are a lot of rules here because I got to tell you how the addition works and how the multiplication works. Now, to save time, rules 1 through 5 are the same as these rules. So the addition has abelian group rules 4 plus. And just for notation's sake, we do identify the E to be a 0. Okay, so we call the identity with the plus 0. Okay? So the first 5 rules, this guy right here behaves like an abelian group. Which is kind of nice that we set abelian groups up first, because then we don't have to rewrite all 5 of those sentences, right? I like not writing very much. Well, contrary to what you see, but anyway. So rules 1 through 5 are the same as abelian group rules, but only for plus. Multiplication doesn't behave the same way, okay? So rule 6 is, we're going to start with the multiplication ones. For A and B in the ring, the multiplication stays in the ring. Also, you have that the operation is associative. Okay? And you get the distributive properties in both directions. What did I not list conspicuously? There's a couple of them. For multiplication, I'm not requiring the existence of an inverse, I'm not requiring the existence of an identity, and I'm not requiring commutativity. Do you know why? Let's think about this. We talked about matrices, right? Okay? If you take matrices that, let's make it easy. Let's talk about square matrices so that there's no question about whether or not we can multiply them. If you take square matrices, we already know that it follows all the addition rules. But its multiplication, okay, if they're square, it does happen to have an identity, but as we already pointed out, it's not commutative, right? So it doesn't have an AB times BA. Does every element have an inverse for square matrices?
No.
No. Okay, so there's an example of a ring. So the square matrices have a ring structure because they have an addition, they have a multiplication, they follow all these rules. The structure even has an identity, but it's not commutative and it does not have inverses. Does that make sense? So we can see these structures occurring in nature in all sorts of other places that we talk about, but they don't always have all of the same properties that the real numbers do. So we make some of them a little bit optional. Okay? So there are 3 additional optional ones here. Okay? Optional. Some rings have them, some rings don't. There is a 1 in the ring, such that A1, which is a great steak sauce, times 1A equals A. Commutativity. Okay? And in fact, if you have commutativity, 9 becomes a little redundant, because I could have moved it in front and done the distribution that way. But if you notice, the order actually makes a difference here. A has to stay in front here unless you know it's commutative, because A was in front here, and C has to stay in it, and to the right here because it was in the right there, unless you know it's commutative. So there's a little bit of funny structure there. And then here the last one is for A and R with A not 0. There is an A inverse in the ring, such that A inverse equals A inverse A equals 1. An object like this is called a unit. Okay? And so what Greg said earlier to try to describe the inverse property, he said that every non-zero element is a unit. So he said that every non-zero element has that property. That's what he meant. Okay? That's pretty cool, right? Started from arithmetic, got to Greg's algebra statement. Right? Okay? Okay. Has anybody ever seen another object that's kind of like this? Some of you might not have. Yeah?
Vector space?
A vector space is an object that's just like this, okay? It has a little bit of a different kind of rules though, okay? So let's talk about a vector space real quick. A vector space, if you go into linear algebra, you'll talk about this. Okay, and it is exactly the same kind of vectors. This is actually pretty cool because, for example, if you talk about arrows with length, right? No numbers involved, just arrows with length, right? Because we know a vector is what? It's an object that has both direction and magnitude. Anybody who's ever seen Despicable Me knows that answer, right? And those that haven't seen Despicable Me need to go watch it now so you understand the reference. Anyway, but to add these guys together, what I do is I define it geometrically. I draw a parallel vector from either one of them, and they end up going to the same point. The vector that points to that right there is what I define as the addition. That addition satisfies all 5 of these rules for it to be an abelian group. Pretty cool, though. There's no numbers involved. You see that? No numbers at all. But the same structure is there. It follows all the same rules. All right, so a vector space, there's one other operation you can do here. I can take a vector and I can make it longer, or I can reverse its direction, right? That's like some kind of multiplication there, but it's not a vector times it, it's more like a number times it, right? Okay? So a vector space is a set V with a, I'm going to use a word here, field of scalars. Scalars just means number. Field is a ring that has all 12 properties. Okay? So a ring that has all 12 properties is a field. The real numbers are an example of a field. The complex numbers are also an example of a field. Okay? So you start with a set V and a field of scalars F. I don't know what field they are. For example, it could be the real numbers, it could be the complex numbers, it could be any other field you want. Anything that follows all 12 of those rules. This field already has the ring structure already embedded into it, so I'm not going to worry about that. I'm going to talk about operations on V. And two operations. There's plus, which takes two vectors and produces another vector. That's like this property. Okay? This is just an example, by the way. Lots of things are vector spaces. For example, polynomials are vector spaces. Okay? They behave the same way. And there's a notion of what's called scalar multiplication, which takes a field, an element of the field, and a vector, and produces a vector. Okay? So it's a little bit different than the other operations we've seen. The plus structure has rules 1 through 5. And guess what it is? It's an abelian group. Okay, so it starts with an abelian group again. Okay? And then the other ones just tell me how this scalar multiplication behaves. So 6 is, if A is in F and U is in V, this implies that AU is in V. That's basically the idea that it actually is a function. This operation behaves like a function. It's associative, which is really kind of curious here because A and B are elements of the field. U is an element of the vector space. Okay? A times B times U actually equals AB U. Now here, this is scalar multiplication in the vector space. This, A times that, is scalar multiplication in the vector space. Over here, this times that is scalar multiplication in the vector space, but inside the parenthesis is what?
Scalar.
It's multiplication in the field. That's kind of curious, right? So there's some weird connections there too. Okay? All right? Number 8 here. You have that distributive properties. This way, which takes distributes scalar multiplication, distributes across vector space addition, but scalar multiplication also distributes across field addition. Does that make sense? Okay? This is addition in the field. Okay? This is scalar multiplication. This is addition in the vector space. See these operations? They're a little bit different, kind of hairy around there. The notation gets a little funky. All right? You have to be a little careful sometimes. As long as it's understood, we keep moving, which I'm going to assume. But, and then also you have one other thing, that for the identity element that's in the field, if you multiply that by the vector, you get the vector back. So the identity, scalar multiplication with the field identity element also behaves as an identity. Does that make sense? And these are the 10 properties of a vector space. Okay? And anything that satisfies these properties are a vector space. Column vectors in R3 behave this way, but so do polynomials of degree 3. In fact, those actually behave in almost in exactly the same way. Okay? Is this making sense so far? Maybe okay, at least just at the loosest idea that there's these abstract objects that are mirroring some of the behavior we see in the concrete ones we sort of started with. That, if you have any takeaway, that's the takeaway I want you to have. Is that we're studying abstract objects that follow the same kinds of rules that the concrete ones did that we started with. Okay? Now, what if I have two different objects of the same type, say two groups? Okay? And I want to have some way of being able to compare them. And this is a little weird. To compare them, what I'm going to use is functions between them. Now, what's a function? Does anybody know?
A linear mapping?
It can be linear, it doesn't have to be linear, but you're right, a mapping is a linear mapping is an example of a function. What's the definition of a function?
We'll begin with
One thing in, one thing out. Exactly. That's exactly right, okay? A function is a comparison of two different sets such that if you give an input, you get an output. And it's guaranteed. You know what the input is, it pins down the output. Does that make sense? Okay, so we're going to have special kinds of functions. They got these cool names called homomorphisms. And they're a special type of function that does the following. For example, in groups, it's a function from one group G to another group H. Both of these are groups, so they have the structure over there, at least 1 through 4 on the group rules, okay? But in both places. So there's an operation in G, there's an operation in H. They might not be the same operation, okay? For example, this could be the real numbers, this could be the Rubik's Cube. Does that make sense? Okay? A function between them that preserves the operation so that if you multiply first and then map, it's the same as mapping first and then multiplying. Does that make sense? Okay? It's a structure-preserving map. So it's a function that doesn't care whether you multiply in G first, then map, or if you map both elements first and then multiply in H. Does that make sense? Multiplication over here is multiplication in H. Inside here it's multiplication in G. Okay? Does that make sense? Any function that has that property is called a homomorphism. For a ring, what do you think it is? From one R, from ring R to ring S, what do you think homomorphism for rings has to preserve?
Addition
Say it again?
and multiplication.
Addition and multiplication has to preserve both operations. So f of A plus B has to be f of A plus f of B, where this is addition in R, this is addition in S. F of AB has to be f of A times f of B, where again, multiplication in R, multiplication in S. That preserves the structure there. How about vector spaces? A map from B to W. What does it have to preserve?
Addition and scalar.
Yeah, both of the operations, addition and scalar multiplication. So it's got to preserve this right here. And it's got to preserve scalar multiplication. In particular, for this to work, for this to work as I've written it, they have to have the same field of scalars. But you can make it work without that too. But anyway, we'll leave it at that point for now. Okay, they have the same field of scalars. That's what a vector space homomorphism is. How many of you have taken linear algebra before? What is that called? A function that has those properties.
Linear.
It's a linear transformation. A linear transformation between vector spaces is another word for a vector space homomorphism. Okay? It's a structure-preserving map. Okay. Now, this just sort of tells you that that you're inserting sort of the behavior of B into the behavior of W in some sort of way. But if the functions don't have certain properties, where did my notes go? Then you don't necessarily have a perfect comparison of everything that's going on. So I need to talk a little bit about functions for just a second. Okay? Those of you, for anybody, what makes a function invertible?
It's 1 to 1 to 1.
Has to be 1 to 1. Okay. Now, when you learn calculus and algebra, that's the only requirement. They're actually hiding something from you. Okay? And what they're hiding is they have purposefully never given you an example where the function was never onto. Does anybody know what onto is? Those that have taken linear algebra have heard of onto before. What does onto mean?
It means where 2 is under whatever you're on.
It means a function is onto if it hits everything in the target space. Okay? If every element here gets hit. Okay? They sweep this property under the rug in calculus. Okay? And they just say that you always are mapping to, what do you call it, the range, right? The range is the set of elements that get hit, right? Well, it doesn't have to be that way. For example, if I talk about a function from R to R, given by this, this is definitely a function, but because I said it's mapping from R to R, does it hit everything here? No, it's only hitting non-negative numbers. So this is not the range. We call this the codomain. This is the domain. This is the codomain. If the codomain equals the range, meaning everything in the codomain gets hit, that's what we mean by onto. Okay? Another word for it is surjective, but F onto means everything gets hit, if you want. This is sometimes also called surjective. Now, the one-to-one property you guys told me is called, well, one-to-one or injective. And what does it mean? Means that if you ever come across two elements in the domain, what'd you say, Greg, that equal each other, that map to the same thing?
Yeah, they map to the same thing, and they have to be the same element.
Right. So if you ever come across two elements in the domain space that map to the same place, they have to be the same element. Does that make sense? That's injective or one-to-one. That's what makes it invertible. In fact, you actually have to have both of these properties to be invertible. It's the only way you can reverse the arrows and talk about the function going the other way. Okay? A function that is injective and surjective is called bijective, and is another word for invertible in the set sense, I guess. I won't even say that. It's just bijective. Okay. Now, this is the types of functions whose arrows are reversible, and you still maintain a function. Does that make sense? Okay. If the function one way preserves the properties, and when you reverse the arrows, it also preserves the properties, this is called an isomorphism. Okay? It essentially means that both spaces behave exactly the same way. It means that all of the operations you do in one space, you can map to doing in the other, and vice versa. So anything you do in one space, you can automatically do in the other by just pushing it through the map, or its inverse. Does that make sense? So if you can find two spaces that have an isomorphism between them, they are effectively, for all algebraic intents and purposes, the exact same space. So for example, column vectors with 3 elements, so R3 column vectors, their addition and scalar multiplication behaves exactly the same way as quadratic polynomials. Okay? Quadratic polynomials have how many coefficients? 3. Constant, linear term, square term. And they don't talk to each other because you can't combine squares with linears, right? So they basically act like placeholders, just like they do in the column, and all the behavior is exactly the same. So they are isomorphic as linear spaces, as vector spaces. Okay? So an isomorphism, F is an isomorphism if it's a bijective homomorphism. Homomorphism. Okay? So if the arrows are reversible and it preserves the structure, that's an isomorphism. Make sense? Okay. One last thing we need before we can get to the cat. All right. And that's the idea of something called a quotient space. Okay? A quotient space, and we're gonna do this kind of simplistic, okay? So the whatever that means at this point, but the quotienting out can be a very complicated process, and I don't want to get into all the hairy details. So I'm going to do it in a very practical, very specific case that guides the rest of this discussion. In all these maps, if I have something that maps from G to H, there's going to be a set K, which is the set of all elements G in G such that F of G maps to the identity in H. Okay? There's going to be a set of objects that do that. At the very least, the identity in G always maps to the identity in H if it's a homomorphism. Okay? So I got to say this is a homomorphism. Okay? This object is called the kernel. Okay? And for ring homomorphisms, there's also a kernel. It's the set of objects that map to the additive identity, the 0. Okay? Vector spaces also have this. The set of objects through a linear map that map to the 0 in the additive 0 in the 0 vector in that space is also called the kernel. But you guys in linear algebra probably recognize the term null space. It's the same object. Okay? The null space is the kernel of those maps. Okay? So this is just the stuff that's mapped into 0. Okay. I could ask how far off of the kernel an object is. And I could argue that two objects are essentially the same type of thing as long as they're just as far away from the kernel as each other. And that's one way of thinking it. So I'm going to define this notion of equivalent mod K.
Would that be a way to define like absolute values?
You probably could set it up so you could define it that way. I'd have to think about it for a second. I don't want to derail this, but no, yeah. Ask me again afterwards, and we can talk about that. So equivalent mod K. A and B and G are equivalent mod K if A minus B, which is A plus negative B, right? Or A, B negative, B inverse, if we're talking about groups, is in the kernel. So if their difference or their ratio is in the kernel, that's what we mean by them being basically the same object mod K. They only differ by an element of the kernel. Does that make sense? If you talk about this kind of thing will actually divvy up all of the pieces of G into little classes that are disjoint. They never have any intersection. Where all of the guys in one of them are equivalent mod K. In the other group, they're all equivalent mod K, and all the way through. Completely delineates the entire space into tiny little classes. Well, what if you considered each of those classes as its own element, as its own object? Okay? So each of those classes, and for the sake of this conversation, we'll call it A plus K. This is the class of objects that differ from A by a element of the kernel. Okay? A plus K. I can actually define an addition on these guys like this. And K has some nice properties that allows that to actually satisfy all the group properties. Okay? So this satisfies the group axioms, which tells you that these classes, these equivalence classes, are actually acting inside as a group. Okay? So it's like I've got a group inside of a group. And if I think about that smaller group on its own, we call that a quotient group. So this guy right here, the classes with this addition, is called G mod K.
When you say mod, does this have anything to do with mod arithmetic?
It
like mod?
absolutely does. It's exactly the same idea.
Would that be an example?
That would be an excellent example of a quotient space. Thanks, Bob. If you talk about modular arithmetic, so those of you that do computer science, you guys have probably seen this in programming, okay? But modular arithmetic is how far off of a multiple of a certain number you are. So like mod 12 is how far off of a multiple of 12 you are. This cuts up the real numbers into 12 objects, right? 12 different classes that are all exactly a certain number off of a multiple of 12, right? And you can add these together and their behavior behaves the same, but now you have a group that's built out of the real numbers that only has 12 elements in it. It's no longer infinite anymore. Sorry, built out of the integers. That's no longer infinite. It's only those 12 objects. And that's called a quotient space, okay? Now, this is a quotient group. You can do this for rings. You do it the exact same way, only instead of using a group homomorphism, you use a ring homomorphism, and you mod out by the kernel in sort of the same way, and you can get a ring mod the kernel. You can do it in vector spaces, and you can get a vector space mod a kernel or a null space, okay? And each one of these objects turn out to also be a group, a ring, or a vector space. Does that make sense? Okay? A little bit, at least at a very loose level, okay? I'm not trying to get too detailed here, okay? Now, what's interesting is that there's this funny little theorem that you run into really early on in the study of algebra, which, by the way, is what we call this. When mathematicians say algebra, this is what they're talking about. It's not the same thing as you guys, as regular non-mathematicians would say when they say algebra. They think of solving for x. But when mathematicians say algebra, this is what we mean. Okay? A little scary
I use up to
sometimes.
1050.
What's that? Is this how you teach 1050, right?
My students think so.
Yeah. Okay. As you study group theory, you run across this theorem here. It's called the first isomorphism theorem. And it says the following. If F, mapping G to H, is a surjective homomorphism with surjective group homomorphism, sorry, with kernel kernel K, different kind of kernel, right? Then the quotient group G mod K is isomorphic to H. Okay, that's interesting. So if the you can always make the quotient group. out of this kind of thing. But if the homomorphism happens to be surjective, then it turns out that there is an isomorphism from the quotient group to H. That's pretty cool in and of itself. Until you start studying rings. And when you get to rings, you find out the following. There's groups, there's rings. There's a first isomorphism theorem there too. And it states the following. If F, mapping R to S, is a surjective ring homomorphism with kernel K, then the quotient ring R mod K is isomorphic to H. Is it just me, or does that sound like I'm repeating myself? Okay. Then you go to vector space, linear algebra, and you find out that there's a first isomorphism theorem there too. And it says that if F, mapping vector space D to vector space W, is a surjective vector space homomorphism, or if you want an onto linear map, then, oh sorry, with kernel K, then the quotient space V mod K is isomorphic to what?
H.
How'd you know that? To what?
W.
Oh, so not H, this should have been S.
The
To
W.
what?
W.
W. How'd you know that?
It's right on
How'd
the
you know what I was gonna write?
So,
'Cause it's the
to
one
make
where
sure
you
I'm
build
with
some
you,
more.
Alan,
It's a lot like that, yeah.
make sure I'm with you, example, if you were going from degree 2 polynomials to degree 1 polynomials by taking derivative,
Yep,
and the kernel is,
constant functions.
Yep.
And then you get an isomorphism from the quotient space to the linear functions.
Degree 2 polynomials, mod constants is,
Is linear functions. And then, okay, really weird stuff, okay? Now, what do you see that's super conspicuous about these theorems?
They all have the same name.
They're all the same.
The first one.
But a vector space and a ring and a group, they're not the same object. They're kind of the same. They have operations and stuff, but they follow completely different rules. But somehow they all have this same theorem. That's weird. When I first came across this, I was like, oh my gosh, that is so weird. There's got to be some kind of connection there. Well, it turns out it's exactly what you said. It's one ring to rule them all. Okay? So mathematicians, when they started realizing that this stuff was happening, they said, I wonder if there's something more fundamental than just operations going on. What if there's a way to abstractify the abstract one more level and try to peel off just what's important about these? What did you notice that every one of these type of objects happen to have?
Function.
Functions, certain type of structure preserving functions. Okay? So they had rules and they had functions, right? Okay? The rules tell you what type of object you have. The functions tell you how to communicate between objects. And so what if we created a class that only kept track of that information? All right. And this is the notion of a category. And we got to the cat at least. Category. A category is a class of objects, which I'll denote with capital letters, and morphisms. What does that sound like? Homomorphisms, right? And morphisms, or if you want, sometimes people will call these arrows between the objects. In our case, these are the homomorphisms, structure-preserving maps that we've seen so far. Category theory actually is really powerful. It can talk about a whole slew of different types of objects with the same language. And so morphisms don't always mean exactly that kind of idea. Every space has its own type of morphisms that are floating around. But in this case, it's exactly those homomorphisms we've seen so far. The morphisms have to follow certain rules, okay? Because whenever you have functions, there's something you can do with functions. If I have a function that maps, if I have a morphism or a function that maps A to B, and I have another one that maps B to C, what can I do with these two guys? I can what?
Compose them?
I can compose them. I can think of the composition G of F, and that maps A through B, then from B to C. So this is a map from A to C. That's an operation on the functions. Okay, so if I'm going to talk about objects and functions, I've got to tell you how the functions behave with each other. So there's some rules on the morphisms. The morphisms have to follow the rules. And the morphism rules are the following. Morphism rules. They have to be, this composition has to be associative. Okay, really, I guess it's composition rules. Rules for composition. The first is that composition has to be associative. So if F maps A to B, and G maps B to C, and H maps C to D, then passing through F and G first, and then doing H, is the same as finding out the morphism that goes from G through H first, and then composing that with that. They have to do the same thing. Okay? So associative property has to be true, and every object has to have an identity morphism. Okay? So there has to be, for all objects, A or B, whatever, there is a morphism, which I'll call 1B, which maps B to itself, such that, now it's kind of a little tricky here because I have to think about this, I have to phrase this function in terms of morphisms because I don't know what type of object this is. Now, it is going to turn out to be the same identity function that you get in all these different spaces. So it would be the function, say, on a group that maps every element to itself. But it's hard to describe that here because I don't know what type of object I have. So I have to describe everything in terms of composition. Such that if I compose, such that for maps from A to B and G from B to C, if I compose these do F first and then the identity, I get F. And if I compose G with the identity first, I still get G. Okay? So it has to be the things that do that. So if you have all that stuff, then you end up getting these things here. Okay? So kind of running out of time here. So I'm going to kind of hand wave a little bit of the rest of this.
Are categories the kind of things like I've heard of with piecewise linear, like polyhedrons, and then topological, which would have homeomorphisms and...
You used a whole lot of words that we have no idea what they mean, Bob.
Polyhedron.
Yes, considering that you're asking the question, I'm betting the answer is yeah, no.
Platonic solids, or...
Yes, there are lots of really excellent examples of different categories that you can mess around with. Okay? Now, so I do want to talk about real quick the idea of an equivalence between objects. Okay? An equivalence between objects is a morphism that has another morphism that goes the other way that sort of inverts it. Okay? So an equivalence is a morphism. Take the cap off, right? Is a morphism from A to B if there's another morphism that goes from B to A, such that whenever I compose them together, this one would be the identity on B, and if I compose it the other way, it'd be the identity on A. So they're the ones that undo each other. Okay? That's exactly, if you think about in college algebra, when they tell you about invertible functions, the definition they give is that they undo each other, right? That's exactly this definition here. We're saying these functions are invertible. That's where we're borrowing this idea. Okay? if you have a function that has this property, then f is called an equivalence between these objects, and we would call those objects in the category equivalent objects. This is the generalization of the notion of isomorphism. Isomorphic objects are equivalent objects categorically. Okay? Does that make sense? Now, the next task is to sort of generalize what this kernel means. Because I'd really like to talk about kernels and quotients and see why that is true everywhere. Okay? So to generalize the kernel, I have to have a little bit more language. I have to have the notion of a, well, I'm going to sweep a little bit under the rug here because we're running out of time and I don't want to get too complicated. Oh gosh. All right. If a category has something called a zero object, which I won't define because we don't have time, but it has some special properties, and this stuff only works if you have one, then there ends up being a unique morphism between any two between any two objects called 0AB. Okay? This would be the object between A and B called the zero map. Okay? And what it does is it has the following property that if I have a map from A to B, I meant B to C. If I have a map from B to C, and I have another map from C to A, then composing F with the 0 from A to B produces the 0 from A to C. Okay? And this way, if I compose the 0 from A to B with G, I get the 0 map from C to A. I think I wrote that right. Oh, C to B, sorry. Okay? So these maps kill the maps. Yes, did I just run out of battery?
You're about to.
That's, there's a charger. Is there a plug nearby?
No,
Is there any
I've
plugs down
been
on that?
looking.
Yeah,
Just right underneath.
Right, fine.
Oh, right here. Here, hand it to me, Alan, and we will.
There it is. Thanks. All right, can you plug that in and get us going? Otherwise, my students are going to hate me because I told them it was going to be on YouTube. And, yeah. Okay. Great. Okay. Now, once you have these objects, you can form the kernel. Okay? So you start off with a morphism. I'm almost done. Bear with me. I do this in 3 minutes. Okay. We'll see. So if I start off with a morphism, F mapping object A to object B, it's a morphism. The object K is the kernel of F. Now, those that are familiar with category theory, I know I'm not using this sort of standard notation, but just bear with me, okay? The object K is the kernel of F if there is a morphism J, which maps K to A, such that the following things happen. 1, if G and H map C to K, have the property that if I compose them with J, they equal each other, then this has to mean that G and H were the same morphism to begin with. Okay? This is the notion of sort of left invertibility, which is the same idea as injectivity. Okay? So this is how you categorize, make categorical the idea of a one-to-one function. This is basically saying the function has to be one-to-one. And then the second part is that if I compose F with J, I get the 0 map from K to B. Okay? This is how I identify that it's actually sort of part of the kernel, that everything is zeroing out as I go through. And then there's one last property, which I'm going to draw a picture for. Okay? So here's K, here's the map J that goes to A, and here's a map F that goes to B. Let's say that I have a map H from some category, from some object D. So this is H mapping D to A, and it has a property such that if I compose F and H together, I get the 0 from D to B. Okay? So this map doesn't survive through F as it passes through. Okay? If I have this, whenever I have this, there must exist a unique. So there exists a unique unique H hat such that this diagram can use, which means that H equals H hat composed, sorry, I did it backwards, equals J composed with H hat. So essentially it means that whatever morphism you have, whatever object you have here, there's a morphism that gets killed through F, you can actually realize it as it first mapping through the kernel and then being put into A. That's what that morphism actually is doing. Okay, does that make sense? If it has all three of these properties, that's what we call the kernel. Now this is kind of weird. This kind of object here, this commutative diagram we call it, is actually how most things end up getting defined in category theory. Because everything has to be defined in terms of compositions and stuff. So you have to sort of viscerally figure out what are the fundamental pieces of there. Now, if you notice, I do have a hat on this morphism, so there's the cat in the hat. And as you can tell, he is a little abstract. Okay, now, quotient spaces are kind of curious too. And if I can draw the quotient space picture, then the isomorphism theorem falls out. So a quotient object, you have to have A mod K is the quotient object of a map. We call this object A mod K if there's a morphism here with kernel K, with kernel of pi being equal to K. So it has to first sort of have this property, okay, with that K there, such that three things happen. The first one is that, you have this kernel, so there's property one. Property two is that this map, when you compose it with functions g and h, be real careful here. G are functions that map A to B, and H maps A to B. Then if they first, no, I gotta be careful, not A to B. They've got to map with pi, which don't, A mod K, sorry. If you have any maps like this that happen to equal each other, then this implies that G and H are the same. This is sort of right invertibility, which is the notion of it being a surjective map, okay? So has to have a kernel, has to have a surjection, and then you get this cool little picture, which is very similar to the other one, but sort of in reverse, okay? So you get this object, you got your K over here, you've got your J that maps it into there from the kernel part, you have your pi here that maps it down into this guy, all right? Now, if you notice, since K is the kernel of pi, the composition of those two is the zero map from K to there. And we've got this funny little object that goes from A to B. So whenever we have this, such that the following is true. So if F mapping A to B is such that F composed with J is equal to the zero from K to B, all right? So that it kind of behaves a little like that. Then there's a unique map, F hat. There is a unique F hat mapping A by K to B such that this diagram commutes. So such that F is equal to F hat composed with pi. And that's what we have as a quotient map. Now, the first isomorphism theorem at this, it becomes really easy. Okay? If this morphism is surjective, so it has this sort of property over here, this second property, then this guy right here is an equivalence. The guy that comes out is an equivalence. That's it. That's the whole first isomorphism theorem. Okay? If this guy happens to be a surjective, then this is an equivalence. But notice, I didn't say anything about groups, rings, or fields, right? Groups, rings, or vector spaces. These objects are already generalizing all those pieces together. So no matter what objects you kind of start with, whatever the rules are, as long as you have the morphisms and you can construct these pieces, the first isomorphism theorem falls out from the definition of the quotient space by a kernel. Okay? It's automatic. And that's why it shows up in every single one of these places. So, moral of the story is, in mathematics what we do is we take things like the real numbers that are concrete ideas and we try to understand what's basic and true from a fundamental perspective, pull that piece out, and then try to figure out what's true from just those fundamentals. And see if we can see those fundamental pieces anywhere else in nature, whether it be a Rubik's Cube, or whether it be, what'd you say, tetrahedron, all that kind of stuff, right? Polyhedrons, right? Whether it be anything like that, anything that has symmetry, has groups in it, right? So we see those things. But as we went along, sometimes mathematicians noticed that there were things that were similar about those constructions themselves. And so they were able to abstractify one level further to look at the sort of skeletal detail inside those pieces, what were making them tick. And then and as soon as you do that, you start to really sort of understand what's going on. Now you can tell, though, that it gets a little complex really fast. And to really understand it in detail, you need lots of time to figure this stuff out. It's no surprise that category theory, which you just got a taste of right here, was affectionately called by its creators abstract nonsense. Gotta be kidding, right? And it's because all these kind of funny things are happening. But once you have all that set up, you can start seeing things falling out that are true in all of these different kinds of spaces. And that kind of power is really beautiful, to be able to really understand viscerally inside what it was that made that true. And that's what mathematics is really about. It's about trying to find out internally what is making all these different things tick. What's making all of this stuff that work? And that's the same question that science asks too, which is why mathematics seems to fit into science all the time. They're always looking for the same kinds of answers. What makes it work? It's all the answer why. Anyway, I hope you guys enjoyed the talk.